This unit we're going to be talking about electrons, and this picture that's behind the screen sort of represents what our current view is of the atomic model relative to electrons. So before we get to that, we have to talk about some of the earlier models and what led us to this belief. But before electrons, we have to understand the electromagnetic spectrum, and before we can do that, we have to understand waves. So this podcast is going to help you understand waves.
Electromagnetic radiation travels through space as oscillating electric and magnetic fields. Light is a kind of electromagnetic radiation, as are radio waves and X-rays. To describe electromagnetic radiation in terms of waves, two components are used, a wavelength and a frequency. This exercise explores the mathematical relationships between the different properties of electromagnetic waves and between electromagnetic radiation and energy. The wave-like behavior of electromagnetic radiation is similar to waves in water. Describing electromagnetic radiation in terms of waves consists of two components, a wavelength, indicated lambda, and a frequency, indicated by the Greek letter nu. Wavelength is the peak-to-peak distance of a wave. Frequency is the number of peaks to pass a given point per second. Lambda nu equals c, which is the speed of light.
Alright, so let's make sure everybody's on the same page. So if I have a wave and I want to know the wavelength, what I want to look at is 2 points. Let's say crest to crest. This is lambda, the wavelength. Okay? I could also do trough to trough, so I could do trough to trough or center to center. Any 2 same points on a wave. Okay? So that is wavelength, and let's make sure we understand what frequency is. So frequency is how many waves go by in a certain amount of time. So let's say I'm plotting this and I have a time axis, which is usually going to be seconds. I can look at how many times this wave goes by in a certain number of seconds. And of course, the frequency of a wave like that is going to be much higher than it would of a wave like this, where I'm going to have fewer waves going by. And when I'm measuring how many waves go by, I'm looking at, again, peak to peak, trough to trough. Okay. And the other thing that was talked about here was that we measure frequency in hertz. So the unit of frequency, let's just minimize that. This is frequency is hertz. And a hertz is 1 per second. So if I'm talking about 37 waves per second, because that's really what I'm measuring, then I have 37 hertz. Okay, so we often talk about frequency. We often use the units hertz, or we'll say seconds to the minus 1, which is the same thing as this. Okay. Okay, so here we have this problem. We're shown a wave, and we want to define the wavelength, frequency, and energy of the wave shown above. Use scientific notation and be sure to check your units. Okay, so this scale does not show units on it, but I'm assuming wavelength is going to be reporting in nanometers because that's what we have here. So we're going to use nanometers. Okay, and if I look at, let's say, crest to crest, 100 to 800, that's going to be 700 nanometers. Okay, so if I want to find frequency or energy, I'm going to need some of my formulas. Now, if you look on your equation sheet, what you will see is that the equations and constants that you need to do this are located on your equation sheet that I gave you. Okay, so there are formulas here. E equals h nu, C equals lambda nu, and we are also given some constants that will be helpful for us. Okay, So I'm going to shrink this down a little bit. And what I know is I have a wave with 700 nanometers, and I want to figure out, I want to first figure out the frequency. So if I look at the formula, C equals lambda nu, right? What I'm trying to find is the frequency. So frequency is going to be C over lambda. And it tells me right here that the speed of light is 2.998 times 10 to the 8th meters per second. And I always use 3 times 10 to the 8th meters per second. Okay? And I'm going to divide that by the wavelength. Now the wavelength here I have is in nanometers, but this is in meters right here. So I'm going to have to convert my wavelength from nanometers to meters. So if I have 700 nanometers, what you need to know, especially for this unit, well, and of course for the exam, is going to be the conversion from nanometers to meters, because we use that all the time in this unit, because wavelengths are usually measured in nanometers, is 1 times 10 to the 9th nanometers are in 1 meter. So that's going to give me 700 times 10 to the minus 9 meters. Okay? So that's my denominator. So when I divide those, I'm going to get 3.0 times 10 to the 8th meters per second divided by 700 times 10 to the 9th meters. And my meters are going to cancel out. I'm going to be, and I punch that into my calculator. Now let's think about sig figs. Now, my constants don't have sig figs. They don't limit us. These are definitions, okay? And if I look back at my graph that I read the 700 off of, let's think about how many digits we can report. So this is the hundredths, the smallest grid line. I can estimate 1/10 of the way between the grid lines. So I really know that 700 to the second digit, okay? So I have 2 sig figs from my measurement, okay? From my measurement. So this is going to be 2 sig 4.3 times 10 to the 14th, and I'm left with 1 over second, which is also, of course, hertz. So that's going to give me my frequency, right? That's my frequency. Now I need to get my energy. So it gives me right here this equation, E equals h nu. Now, h is Planck's constant, and that is given to me on the equation sheet. So I'm going to take Planck's constant, 6.626 times 10 to the minus 34 joules seconds, times my frequency, which is 4.3 times 10 to the 14th, 1 over second. And here the seconds will cancel. I'll end up with a unit of joules. And if I multiply that out, I get 2.9 times 10 to the minus 19th joules. So this is my energy. This is my frequency. And I had 700 nanometers. Okay, so we're going to stop it right there.